Hello students, in today's lecture we'll discuss about the ADC and DAC interfacing with the 8051 microcontroller. Students, you all know the physical quantities like temperature, pressure, humidity, water level, all these can be monitored using the microcontroller. In different applications, we use the microcontroller. Mainly 8051 is the 8-bit CPU optimized for control applications. So what we need, the physical quantities, those are to be converted into the electrical signals. And you all know that is done using the transducers or sensors, like the temperature sensor, pH sensor. So different sensors that are used to convert the physical parameter into the electrical signal, and those electrical signals are in the analog form. So we need to convert it into the digital form to apply that as an input to the microcontroller, because you all know microcontroller is a digitally operated device. So for that purpose, A to D converters are used for converting the analog input signal into the digital form. So first of all, let us focus on the A to D converter. The ADC that we are going to discuss is the 0808, which is the 8-bit A to D converter. It is having total 8 channels. That means at a time 8 different parameters that can be monitored using this single A to D converter. Here you can see in the figure that the analog input is used as an input to the through the sensor. It is used as an input to the A to D converter, and then we'll get the digital output in this way. So that is the basic concept of this A to D converter. Let us see how this A to D converter 0808 that functions. For that, let us understand the various signals that are available on this 28-pin chip. Here we can see the input side where in 0 to in 7, these are 8 analog input signals. What are the channels? A, B, C. These are the 3 address inputs that are called as the channel selection. Depending on the status of A, B, C input, one of the channel out of the 8 gets selected. ALE is used for latching purpose, and here is the input to the A to D converter to start the conversion. So whenever you want to give the start command, this signal should go high. The clock, that is external signal used for A to D converter. Here are the reference voltages, plus and minus. Those inputs are there. Then at the output side, you will find the digital output D0 to D7 bits. Out of that, D0 is called as the LSB or LSD, least significant digit, and D7 is nothing but the most significant digit. Then this is the output signal called as the end of conversion. Whenever the ADC will finish the conversion, this signal will automatically go high. Then there is output enable signal that is used to read the digital output available on these data lines D0 to D7. Then the VCC and ground are nothing but the power supply connections. So that is about the ADC 0808, the various signals. Now here we can see in this table how these ABC inputs that are used for channel selection, in that you will find that from 000 to all ones, that is used for selecting one of these in 0 to in 7. So one channel will be selected. Let us say, suppose if the status of ABC is 101, then channel number 5 that will be selected, right? So 8 analog input channels which are multiplexed and selected using the 3 address pins A, B and C. Next, here is the description about the various signals that we just discussed. Address latch enable should go low to high, and then one of the channel will be selected based on ABC inputs. Then the start of conversion pulse, then end of conversion and output enable. Next, let us discuss about how it is interfaced with the 8051 microcontroller. On the screen, you observe the interfacing diagram. There, the 8051 microcontroller chip, which is interfaced with the ADC 0809. Here, you can see the P1.0 to 1.7, those are nothing but the data inputs. D0 to D7, the data output that is available at the output side of the ADC, that is taken here for port 1. So port 1 is used for that data, that is the input port. And here P2.4 is the address latch enable signal. However, here INTR means the end of conversion signal, that is on P2.7. Okay. The clock is generated using the quartz crystal on chip clock oscillator, and here you can find D latches used to obtain the required frequency that is applied as a clock input to the A to D converter. Here you can find the RD and WR, that is read and write signals. Write signal is used for start the conversion, and the read signal is used for reading the output available on the D0 to D7 lines whenever the conversion is finished. Here you can see the reference voltage that is set to 2.56 volt. And now here are the input channels to the A to D converters. In 0 to in 7. Out of that, in the figure, channel number 1 in 1 is used here for applying the analog voltage. Using the potentiometer, we will vary that, say let us about 0 to 10 volt, and equivalent output will get on these D0 to D7 lines after the ADC will finish the conversion. The chip select, that is permanently connected to ground. So that is about the interfacing of the 8051 with the A to D converter. Now, same circuit is shown here, only thing is that whatever the input for the clock, the latches that are not shown here for your simplicity. So clock is externally applied to the A to D converter. Well, going to the next, as an example, let us discuss about the temperature sensor, which is used for temperature. That is, the temperature is the physical quantity which is converted into the electrical signal using the device called as the thermistor. Well, the widely used temperature sensors that includes the LM34 and LM35, because that doesn't require the external calibration. So since it is having the internally calibration. So for LM35 precision integrated circuit temperature sensor, whose output voltage is linearly proportional to the Celsius temperature. That means from 0 degree Celsius to we can monitor equivalent voltage that is we'll get from these sensors. It does not require the external calibration, and it outputs 10 millivolt for each degree of centigrade temperature. Means for 1 degree Celsius, the output will be 10 millivolt. That can be understood here. Here you can see you need some signal conditioning before the analog input is applied to the A to D converter. Whenever we'll take the external physical quantities from external world, temperature, pressure, etc., sensors will convert that into the electrical form, and here you need some signal conditioning, because as the signal travels from one device to other device, the signals become weak during their path. So to bring to them required level, you need some amplification, and that is called as the signal conditioning. So different amplification and buffers that are used to bring the signal to the required level, and then they are applied as input to the A to D converter. The ADC will give you the digital output, and then it is applied as input to the microcontroller. Here you can see how that thermistor from this table, let us say suppose if the temperature is 0 degree Celsius, you will get the 0 millivolt, and what output you are going to get is nothing but the 0, 0, 0, 0 on the D0 to D7 data lines. If suppose the temperature is 1 degree Celsius, you will get the output 10 millivolt. If it is 2 degrees Celsius, you will get 20 millivolt. If it is 3 degrees Celsius, you will get 30 millivolt. So linearly proportional output voltages we are obtaining from this sensor. If it is 10 degrees Celsius, we will get the 100 millivolt, and similarly for 30 degrees Celsius, you will get the 300 millivolt. And equivalent digital outputs you will obtain on D0 to D7 lines, that is shown here. Well, since the ADC is the 8-bit, there are total 256 steps, and LM35 that will produces 10 millivolt for every degree Celsius temperature change. We can condition V in of the A to D converter to produce a V output of 2.56 volt for full scale output. So the V reference that is used is 2.56 in our interfacing circuit. Here is the use of the LM34 or 35, the temperature sensor. You can see here it is connected to the channel 2. The rest of the circuitry is same, whatever we discussed. Either ADC 0808 or ADC 0848, 0809, all are same, belongs to same family. So don't confuse. And here through this port we can vary the input voltage, right? So from the channels you will get the analog input converted into the digital output. Say 0 volt to 10 volt, you will get the equivalent digital output over here. That is how the A to D converters are interfaced with the 8051 microcontroller. Now ADC will be used at the input side of the microcontroller. However, once the microcontroller process that input and gives the desired output, that is in the digital form, but to the external world, that should be converted again back into the analog form, and that work is done by the D2A converter. DAC will take that digital input from the microcontroller and will convert that into the equivalent analog, and then it is given to the external world. Here DAC 0808 that is used, which is again a 8-bit D2A converter. The IC converts digital data into equivalent analog current. Hence, we will require a current to voltage converter, I to V converter, to convert this current into equivalent voltage. DAC will provide 256 discrete voltage levels of the output. So this MC1408 or DAC 0808, the digital inputs are converted to current, and by connecting a resistor to the I output pin, will convert the result to voltage. The total current provided by the I output pin is the function of the binary numbers at D0 to D7 inputs of the DAC. And the reference current, I reference, that is as follows. When D0 is the LSB and D7 is the MSB for the inputs, and the I reference is the input current that must be applied to pin 14. The I reference current is generally set to 2 milliampere. Here is the formula that is used for calculating the output voltage. V out equal to V reference into, here these are nothing but the digital D0 to D7 inputs, bits, and D0 by 2, then D1 by 4, D2 by 8, D3 by 16, D4 by 32, D5 by 64, D6 by 128, and D7 by 256. Summation of all this into V reference voltage. For an example, if suppose the input data is 0, 0, that means the digital data is all zeros, and reference voltage is 10 volt. In that case, what the output voltage you are going to get is 0. If we consider another example where the data is 80, and now again reference voltage is 10 volt. Here you can see only MSB bit is 1. So only MSB bit is 1. Sorry, here there is a mistake, I think. So here you will get the output voltage 10 into 1 upon 2. So D0, actually this should be D0 bit, and this is the D7th bit, right? So you will get the 5 volt as the output voltage. That is how for the corresponding digital input using the D2A converter, we will get the output equivalent voltages. Here you can see the interfacing diagram of the D2A converter with the microcontroller. Again, port 1 that is used, P1.0 to 1.7 as a output port. The digital input that is applied here to the D2A converter, and then at the output of the DAC you will find an operational amplifier that is used as a current to voltage converter. So you will get the equivalent output voltage that can be read out here, right? We reference it's connected here through this 5K resistor to the 5 volt, and we reference negative that is connected to ground. So that is the simple interfacing for D2A converter. Whatever the digital input we will apply, the DAC will convert that into the analog form. That output will be in the current. Then we need to convert that into the voltage using the op-amp as a current to voltage converter. So that is about the D2A converter. So friends, we today learn about what is ADC, what is DAC, how the ADC and DAC that are interfaced with the microcontroller. So normally in any data acquisition system, you will need this ADC and DAC because the microcontroller is mainly used for control applications. You know, many different applications like the temperature controller, pressure monitoring, or in the remote controls of home appliances. You can see for, let us say, remote control of your television, washing machine, dishwasher, the internal processing of that machines, all those are electronic circuits that are nothing but using the microcontrollers. And another example you can find in the vehicle security system or in the traffic controller where the microcontrollers are used. In the industry, mainly the PLCs, programmable logic controllers, where the microcontrollers are used for monitoring the different parameters, controlling the different parameters through the PLC, say in the process automation plant, right? So mainly the microcontroller chip is used for automation purpose. So that is how the ADC and DAC that can be interfaced with the 8051 microcontroller. Thank you.